Hello and welcome to a short presentation on terrestrial forensic geophysics. My name's Jamie Pringle, and this is part of a collaboration with Chris Wisniewski, Ian Stimpson and Viv Heaton, all at Keele University, and there's some more contact details for you there if you're interested. I'm going to talk briefly about some major forensic geophysical methods, some pictures here using a radar on the left hand image in Cannock Chase in the Midlands, and then the right hand image is some master students and myself collecting some wildlife forensic geophysical data. So by the end of this presentation, you will hopefully know some basics of how to locate targets geophysically and know how some near-surface geophysics can aid archaeological and forensic investigations. And we're going to cover some typical geoforensic applications. There's a lot more, but I've only got 20 minutes, so can't cover too much. And ideally, we're going to show you sort of how you do things in a sort of systematic, scientific way, something called standard operating procedures, which police practitioners use to try and make sure you have your best possible chance of forensic detection. Okay, so some typical search methods. It's not all geophysics, of course. There's a lot of other techniques you could use. For example, specialist dogs used for search, particularly for humans. They're called cadaver dogs. This one on the right side, though, he looks like he's got some boots on, so he's obviously going through broken ground. You could be using thermal imaging, perhaps, from sort of handhelds, drones more recently, or helicopters, for example, looking for recent buried or surface remains. You could walk over sites. You could physically probe lumps and bumps, which is what the colleagues on the bottom right image are there doing on saddle with more with some sort of metal probes, augers type thing. Or you might be looking for vegetation changes or entomologies or bug changes, maybe locating around a particular site. So geophysics is one of complementary techniques. Some advantages that I've listed for you there. Hopefully it doesn't disturb the ground too much, and you're basically pinpointing areas for follow-up other investigations, whether they're intrusive or other techniques. So it's relatively rapid. It doesn't feel like you're collecting it sometimes, and hopefully you're going to keep the forensic evidence intact when you're doing your surveys for the subsequent workers. Okay, so some geophysical basics then. You can have either active methods, which will use some sort of technology. They'll pulse out some sort of signal into the ground and the surrounding area and measure the response. Or there'll be some passive methods. And passive methods measure local variations dominantly in the magnetic and gravity fields, which gravity fields are rarely used in forensics, but magnetics will be. In each of those techniques that we're going to talk about, depends which one you're going to use, will depend on a few factors, like the target, the local depositional environment, the ground conditions, the soil type, for example, the target size, and then there's different kit that you could use in the same techniques depending upon some of those factors. So here's some typical forensic targets that I've listed for you here. There's obviously other ones. So graves, clandestine, that's where you're trying to covertly hide them, if you like. Can be of all ages, tends to be single in the UK, but you'll listen to some colleagues later on in the day talk about mass grave searches in other countries. Is it a fresh one? Is it an old one? Are they buried shallowly or deep? Or even are they primary or secondary? And you need to try and find maybe some primary graves who've had those cases before. So all of those things, there's some variables, obviously. 75% of UK graveyards and cemeteries are full. So again, looking for where there are people are in unmarked graves, or maybe where there isn't anyone where they could be used then to bury people. That's quite important. So burial ground surveys are quite common. Other things of interest: buried weapons. That's always useful for the police force if they normally need that if there's been some sort of a target or something. So that's really important. Other things: money or stolen goods, that sort of thing. Increasingly environmental, illegally buried waste. Again, that's quite lucrative for criminals. Again, trying to detect where it is, how big it is, and ideally when it was in place is quite important. So, but all of this predisposes geophysics being used if there's a measurable contrast between your target and the background material. And if we're just talking about clandestine graves, a static archaeological target shouldn't change, but you will have a temporal or time change issue with a forensic target. So this figure example shows a person in a clandestine burial. You'll see the obvious grave cut, disturbed material, maybe some relic excavated material as well. So maybe a site walkover may find this. Then after sort of days to weeks, you may the body will let off detectable methane and volatile organic compounds. Maybe a search dog might pick that up. then sort of weeks to months, the body will decompose. It will let off that sort of conductive soil water around the grave itself. Vegetation starts to grow, porosity will start to change around the soil above it, and then finally, if it's skeletonized, you'll just have a bit harder to find, obviously. Have vegetation growth, maybe it's ground depressions, and maybe radar might pick that up. So again, different methods may work best for different time frames. So that's something important to think about when you're designing your survey. So bulk ground connectivity is a commonly used first phase of geophysical investigation. It's relatively rapid. You can see here on the theory figure on the left-hand side, you're pulsing out a electromagnetic wave from a transmitter coil, and then you're receiving the remnants of that primary field, and then any secondary fields that get produced by anything that's locally to that area, a knife in this case. That's quite useful. Looking for things like undisturbed versus disturbed soil. And this example on the right is a classic case from Nobes 2000, where they're looking for Yvonne. A lady went missing, and there's some intelligence to suggest she'd been buried in a wood. So it's relatively small survey size, as you can see there by the numbers of that data set. So they collected data on a grid pattern and then mapped that out. So you're looking from above in this example, and then you can see the sort of data is just in grayscale, unfortunately, but the high conductivity data is the white, and the black is low conductivity. So there's quite a few blobs in there, and she was actually located in the area we've highlighted with the red ones. But of course, there's other blobs in there as well. So I think they use radar as well to ground truth some of these anomalies. That's often used in multiple techniques. So metal detectors, they do detect metal, but that's because they're conductive. So they're sort of more like a conductivity meter. So it's an EM thing again, but you notice there on the theoretical figure on the right, the transmitter and coil are almost on top of each other. That'll actually reduce your penetration depth. The wider the spacing, the deeper down you see, sort of crudely, depending upon what site you're looking at. So you maybe only see half a meter or a meter down, but it depends what equipment you've got and what the site's looking like. But that's often really useful to detect where any sort of near surface sort of conductive or metallic objects might be. And the more posh versions can actually discriminate between different metals, perhaps. There's ones you can have underwater, but Alistair will talk to you about that in a different presentation later on today. There's my colleague here, Lawrence Donnelly, collecting or sampling an area within sort of a set area within those white lines, if you can see that on that side. Okay, and this is a no-body case, so actually doing a geophysical survey to confirm that something isn't present is often more common than actually trying to find where someone is. So police had some intelligence in this Midland area. Someone might have been buried, so they wanted to confirm that there was or there wasn't someone there, but so this is where we got involved. So we're in a specific area, it's quite remote, wooded, as you can see from the photograph there. Quite a tough terrain to get to and to survey. So and unusually, they thought it was going to be a vertical burial. So most clandestine graves are sort of horizontally deposited, whereas they thought this was a vertical one. So that's going to be a bit harder to find because it's got a smaller sort of footprint, if you like, from above. So you're going to need a tighter grid spacing of your sample points. So we actually used a specific EM system in this specified area after some initial metal detector surveys. And in fact, this particular instrument, a CMD one, actually has 6 cores rather than 2, so you could effectively get 3 different spacings or depths of penetration. That's why there's 3 plots of data you can see there. So there's sort of red high conductivity colours and blue low ones, as you can possibly see. And as you go through the data, you can see some things are consistent, like the bottom right, for example, is consistently high, whereas other ones seem to be changing, and that's because they're not going through all 3 depths. We then combined the data. We did some radar over some of these areas as well, and then dug the most promising one, which had multiple different techniques pinpointing the same position, where in fact it wasn't actually a body there. So that was a successful result, if you like, because we confirmed there wasn't a body in that specified area, and Chris has worked that up if you're interested to read about it. Okay, so electrical resistivity, that's the inverse of conductivity. It's based on physical probes in the ground measuring a current, so it's actually less affected by above ground interference, which conductivity surveys sometimes suffer from. That's quite useful, and again you're going across a sort of grid pattern, I guess, on a survey site, such as an example shown here. trying to detect where things are more or less resistant. So this is from the University of Arkansas example. So the top image shows you the map of the known graves, the sort of the grey rectangles, and then the bottom image is the resistivity data of the same site. So you can see sort of there's 3 in a row on the left-hand third, showing where they might be. But there's also some other ones which aren't marked on here. So again, it's quite good in that sort of low resistance. Maybe that's disturbed soil in a grave, for example. So that's quite a useful method of looking for things at a slightly better resolution usually than the conductivity meters. And generally, you can actually look at different depths as well by varying the spacing of your probes. And so a little case study on resistivity then. So we were approached by a North Wales Police Service to help them to try and locate a potential murder victim that may have been buried in a rural area in North Wales. So we had some intelligence to suggest what size the victim was, what the potential burial style might be. She might have been wrapped in a suitcase. We had some suspected fields to look at as well. So we did some desk study to work out what the ground conditions were like. We did some reconnaissance work as well. Found the soil was very clay rich, so that suggests not to use radar for reasons I'll go into later. So we used resistivity instead. And then we also looked at our simulated control work to see what the resistivity response would look like in that scenario. So we had 3 very long days collecting data on a series of grids. Here's one shown here. And the software that we used, you can actually get rid of certain trends in the data that we're less interested in, and it also automatically sort of gives you anomalies that you could actually quantify or try and compare with. So you can see there's lots of numbers on here in different blues, so low resistance, and reds, high resistance blobs. And looking at our control data, we tried to work out which ones were most likely to be potentially target, which is why some of the numbers are in red. And once you try and combine all the different grids, as you can see on the plot here, you can sort of build up a picture of the survey area that we were specified around an entrance gate, and trying to prioritize which ones would be most likely that the person might be buried in, as you can see by the sort of large red numbers. There's other sort of bigger blobs in there, but they're likely to be too big to be an isolated grave. There might be changes in soil type perhaps, or near the side of the grids. You have sort of grid edge effects as well if you're gridding data up. So that's very useful to give you sort of a select numbers that you then want the intrusive investigation teams to analyse. In the end, she was actually buried in the next field, so not ideal, but there was a success in that case. And in fact, we've recreated this scenario as an educational e-game. So this is where at lunchtime you can get involved and be the virtual me and run around. Well, do the desk study, run around, do some reconnaissance surveys, and go back in the van and then go and collect some secondary geophysical data, and then trying to work out where someone might be. And we've sort of varied the target burial site each time you log in, just to make it more interesting. So that should hopefully you'll enjoy that a bit later. So this is some control work that I showed, that I briefly talked about just now. This is on our campus actually. So we've actually buried some not pretend people, but some pig carcasses, a naked pig and a wrapped pig, as you can see by the plot on the top right, and then surveyed them over time to see what the signature look like over time. Does it vary? What sort of methods do you want to use? So this is before we've buried it. And then as I cycle through, you can see the days after burial on the bottom left plot. You can see there's, for example, here, this 112 days, you've got a very large, low resistance around the naked pig. That's probably because the decompositional fluids are moving around it. Whereas the wrapped pig is quite harder to see. It's like a small, high resistance blob on the right-hand side. But this does vary over time, as you can see here, which again is interesting. Why is that? Could be the ground's drying up or getting wetter, depending on what time of year you're looking at. And of course, as the body starts to decompose, you're losing that fluid. It gets more skeletonized. The background soil is getting similar to the control area further around it. So that's quite handy data to compare with actual case work that we just talked about, and also maybe saying, well, which technique would you use or which wouldn't you use, and when would you do your survey if there wasn't a time limit. So for example, here it looks like winter surveys seem to be better. And rather than just saying that, we can actually look at the anomalies themselves. So that's what the plots on the left is trying to do. So we can have some software to actually quantify or sort of measure the size of those anomalies. So you can see it both in 2D from above, and then sort of like a little do the 3D one. And on the right hand side, we've sort of plotted sort of time along the bottom and the size of anomaly on the left hand side. You can see it's a cyclical, goes up in the winter, down in the summer, up in the winter, down in the summer, but it's gradually decreasing in size over time, so it's gradually getting harder to find. So again, that's useful information to tell search teams, and also when to do your survey if it's more of a cold case. That's useful, but then of course we don't have that control data over longer periods, which sometimes you're looking for people. So other researchers have looked at things like looking for graves in graveyards. You sort of know where they are because there's usually a headstone. So for those examples, you can actually survey known graves with known burial ages, assuming no one's moved it since then, I guess. And then you can see, right, okay, how does the response change over time, and is that will push back your sort of burial information. So you can see here on the right hand side we've got some resistivity data of different graves, and it looks like it's going down in a linear fashion over time, over 30 years in the same type. Having issues with graveyards, of course, your grave tends to be deeper buried than in a clandestine grave. You've got a bigger grave, sort of grave soil, I guess. You may have headstone and footstones, maybe they fall over as well over time. You've got different material in the actual casket. We've got the casket as well, which has got different materials. So again, there are issues trying to compare that with, but it's better than having no information. So ground penetrating radar then, that's the most commonly sort of used geophysical equipment, generally used for everything from landmines from the 1970s to some more geotechnical investigations, looking for leaking pipes, pavement issues, civil engineering, that sort of thing. So is used in forensic areas as well. You see things in real time as on the screen as it comes in, which is an advantage. It picks up some relatively small things depending on the antenna frequency as well. You tend to see, just an example on the right hand side, you don't see sort of a physical object. You'll normally see a sort of half moon shape, we call it, or half hyperbolic reflection events, a posh word. It's an electromagnetic method, and as you approach your target, it takes less time for the wave to go down and get reflected back, and as you move further away, it takes longer, so you'll get that sort of half moon shape, if you like. It doesn't tend to work too well with clay soils, as I mentioned with the Wrexham study, or in fact salts as well. So here's some control data. Looking over our site at Kiel, we've got relatively low frequency on the left and high frequency on the right, and you'll notice some big half moon shapes on the low frequency stuff. It's actually quite hard to see with the high frequency stuff on the right. So in fact, in this case, you might actually suggest that low frequency is better over time. Although it does change over time, and again, the naked pig gets progressively harder to see as you get less of a reflective contrast, whereas the wrapping gives you a nice reflective contrast throughout. Of course, there are other scenarios than earth cut burials. So this is a paper from Alistair Ruffle, where there's a simulated clandestine burial using a pig, I think, again, under a patio, and they've basically surveyed it repeatedly over time using different frequency of radar. So that's the data on the bottom left. And actually, in this case, the arrows show where the pig's buried. So the mid frequency looks like to be better than either low or high frequency. And rather than an obvious half moon shape, you actually see more of a depression, which you can see on the bottom right schematic. It's possibly you're picking up the air gap as the chest cavity and soil collapses or compresses, rather than the actual pig itself. Some of the sort of issues with graveyards, though, as we've mentioned, not everyone's buried in the right place. You certainly see that in some data. This is some data from a graveyard in Kiel Church. You've got actually the second person in that right-hand grave is not actually buried in the right spot. Or on the right-hand data set, looks like the grave headstone has actually fallen over and then got covered with grass. You're actually picking up the slab rather than the actual grave itself. So you've got some other issues using those sort of data sets. And if you look at some, once they've excavated sites, often they're developing graveyards to put community halls on the side of the church or whatever. You can actually see there's quite a variety in burial styles. So the example I showed you earlier, that's not always true. You can have people slightly different places, or you have maybe they're lined perhaps, or there's multiple people, or there's sort of a more memorial style, or in fact there's people where there aren't any information for. And all of those will have slightly different geophysical characteristics, as we've shown you below that schematic. You've got resistivity responses, magnetic responses, and then some examples of resistivity profiles showing you some of those characteristics. So magnetics then, that's sort of a passive method. You're measuring either the Earth's magnetic field, or with this data set, you're measuring the susceptibility of the ground with magnetic minerals. And you can see this is from a RAF, old RAF base in East Anglia, where they've found an Anglo-Saxon grave. So they've superimposed the grave excavation on top of the magnetic data on the left-hand plot. And you can see there's sort of red, high, hot colours around the grave versus sort of lower, blue, colder colours around it. So that's quite useful. And interestingly, there's no actual metal in the grave, so that's still picking up as a magnetic high feature. And then for more obvious forensic targets, magnetic data, you're going to pick up sort of that quite well. So again, this is collecting on a quite tight gridding up the data, and you can see there's some fairly obvious targets. It's not always just a high value though. If you notice number 10, for example, the ammunition box, you've actually got a low and a high associated with that target. And you'll often see that with magnetic or gravity data. You'll see a dipole. So you're looking for both anomalies, not just the one. So finally, talking a bit about other targets, environmental forensics, that's really a big problem. Illegal landfills, fly tipping, costs a lot of money, as you can read there. It's quite lucrative for people taking waste and then dumping it. So again, that's an area that geophysical surveys are increasingly being used for. Don't have time to talk about it really. And the other thing, even wildlife stuff as well. So this is a local case we looked at, illegal filling of a badger set. So we collected some radar data over the area, trying to quantify how much was filled and where it was filled, so again to help the Crown Prosecution Service. So different examples. That's Chris's paper he's worked up. So going over this short presentation, talked about the importance of trying to be scientific, going through things in a sequential way, and again there's a little workflow there for you to read while I'm talking. Going through sort of large-scale remote sensing methods, down to desk study stuff, reconnaissance, full surveys, and then some sort of ways to finish. So near-surface geophysics is one method of many, which we've briefly talked about. And again, depending upon what you're going to use, will depend what the target is like, what the background's like, and maybe you'll be using other methods as well. So certainly that's an increasing area of interest of research to try and help with both active cold cases, environmental cases, or wildlife cases, as I've talked about. So thanks for listening.